Welcome back to Engineering Acoustics. Hi, this is Professor Ryan Harne. In this video, we'll learn about a concept called the method of images, which is a way of studying the direct and reflected sound fields from sound sources placed near interfaces.
So let's get started. We've seen so far that the pressure amplitude doubles at the boundary when the wave is incident at a rigid interface. So for this spherical source in air, when the waves arrive at the interface, they're doubled at the interface. And we can kind of envision a case when our source moves closer and closer and closer to the rigid interface. It's almost as if then we have two sources right next to each other at this interface, one on top of the other. They would also double their pressure. So we ask, can we apply this concept when the source is anywhere in the environment? In fact, we can if we look at the continuity at the interface. If the interface is rigid, it's not going to move. And two things then need to be true. The pressure needs to be continuous, and the normal particle velocity needs to be zero, since the velocity of the surface is also zero. We look at the direct path, r minus, and the reflected path of the wave, r plus, and we get an idea. The idea is to introduce a source that's mirrored with respect to point 1 across the plane x is 0. The path that this source takes is also r plus the total length, because the incident and reflected waves are the same, and geometrically, if the image source is mirrored from point 1 across plane x, r plus in the purple path is the same as r plus in the blue path. This technique is called the method of images. It applies not only to rigid surfaces, but also to absorptive surfaces. Let's look at the math to see how this works. The acoustic pressures of the point source and of the image source are as follows. The point source acoustic pressure P sub D is A on R minus, where we use a real valued A for simplification, E to the J omega t minus k r minus. And the imaged source, the reflected path, is r, p sub r, is equal to a divided by r plus e to the j omega t minus k r plus. Now, by using the distance between points, we know that r minus is equal to the square root of z minus d squared plus y squared plus x squared, where y is into the page. And r plus, by a similar formulation, is the square root of z plus d squared plus y squared plus x squared. We can find a special example occurs when r is much greater than d cosine theta. In this case, we can approximate our radial distances. R minus is approximately equal to R minus delta R, and R plus is approximately equal to R plus delta R, where delta R is d sine theta. When we work this out, we find that our acoustic pressure in the field point at location r, theta, and for all time, is equal to 2a on r, e to the j omega t minus kr, and then cosine of kd sine theta. This is actually the same as for a point source pair. Although before we had a d on 2 distance to a common plane. We also note that the acoustic pressure does in fact double at the rigid plane. And we note that it's actually double everywhere in the field, just as it is for the reflected and incident field when combined. Let's look at this more carefully. Here, we have a spherical source of waves at the left. It generates waves above a rigid plane, and we see the incident and reflected fields. The wavelength is small, so that there's a lot of time that passes from the incident to reflected waves to the same field point. On the right, we have no interface, and in fact the simulation takes air into account at the top and bottom fields. The ultimate fields, though, on the top are the same, whereas we note that this space is mathematical only. It exists in the sense that it satisfies our boundary conditions and helps us predict the space of the field at top. But it otherwise doesn't actually exist in terms of analyzing the sound field. Now, this is the case when the wavelength is very long, but when we satisfy that r is much greater than d cosine theta example, the wavelength is long with respect to d. And in this case, we see the doubling of acoustic pressure. First, we see our source in the free field and how it radiates spherical waves. Next, when that source is placed to a rigid plane, the wavelength is longer than the distance d from the source to the plane. And in this case, we have doubling of acoustic pressure into the field. And when we replace the rigid interface with an imaged source, we reconstruct the exact same field, at least in the space above the original interface plane. In fact, acoustic reciprocity also holds for this case. If we replace the location of our point source and receiver, what we find that the image switches as well, and the paths of travel for the reflected wave from the original source and from the image source always remain the same. So this shows us that reciprocity applies to reflected and diffracted waves as well as to incident waves. This method of images can be applied to multiple rigid planes. So near the intersection of two rigid planes, there are multiple reflected paths from the source to the field point. We see the direct path here. The first reflection against the plane x is 0 leads to an image that is mirrored by a distance in x dx and a distance in z dz, so that it results in the same reflected path as the actual reflected path from point source 1. Now, a mirror across the plane z is 0 shows that we can introduce image 2, and we see the reflected path from the original point source and the path between image 2 and the field point. But there's another possible reflected path from the point source 1 to the field point, and that's if the wave reflects off of both the planes x is 0 and z is 0. In this case, we identify a third image source. It's imaged across both axes. Now, originally, for a single rigid plane, the acoustic pressure was doubled in the field point. In this case, we've discovered there are 4 effective acoustic sources. So the acoustic pressure amplitude increases by 4 times when there are 2 rigid planes creating an edge. So let's summarize the case of acoustic quantities changing by this baffling phenomenon. And we don't mean a sense of confusion. A baffle is a rigid boundary that's much greater than the wavelength. So let's create a table. We've got a case. In this case, we've got a free field sound source. This change of acoustic pressure amplitude is a 1 times change. There is no change for this case. And the change of intensity is also 1 times. Let's consider the example of a rigid plane. One rigid plane, or baffle. In this case, the acoustic pressure doubles by 2 times. indicating that the acoustic intensity increases by 4 times. Now, when we have a source near two rigid planes, also called an edge, our acoustic pressure amplitude increases by 4 times, like we've just seen, so that the intensity changes by 16 times. And then finally, if our source is placed in the corner of a room, 3 rigid planes or 3 rigid baffles, corner, our acoustic pressure amplitude we'd find would increase by 8 times and our intensity by 64 times. This tells us why for reproduction of music and announcements, speakers are oftentimes placed near edges and corners of rooms to better magnify the amplitude of acoustic pressure that's radiated into that space. So let's summarize what we've learned. We've seen that the method of images shows that sound sources near reflecting planes increase the pressure delivered to the field in a way analogous to simply having more sound sources. Each reflection corresponds to the presence of an image source on the opposite side of that rigid plane. And the method of images is extensible to any number of rigid planes, positioned arbitrarily with respect to the source.
That's it for this video. In the next video, we'll begin to learn the basics of wave propagation through periodic media.